Ladies and gentlemen, we're running just a couple minutes over, which might push back the tracks just a couple minutes, but we're doing great so far. I'd like to welcome Dr. Bruce Jakosky. He is the principal investigator for NASA's MAVEN orbiter. He's going to give us some updates and latest news. So I'm happy to present Dr. Bruce Jakosky.
We're about to find out. Thank you. It's a real pleasure to be here. It's always fun to talk to people that know how to spell Mars and have a real interest in it. Listening to that last discussion, I want to start by just saying a few words connecting up what MAVEN does to the potential human mission to Mars. And that is, the Mars mission, Humans to Mars, is what I think of as a medium to long-term goal. Short-term, today we're carrying out a Mars program. It's the robotic program. And the goals of it are to understand the science of Mars and to learn what we need to learn in order to send people to Mars. So I'll talk a little bit about the MAVEN mission. Can we kill the lights a little bit? It'll make the slides a little bit easier to see. And by the way, Casey, if you're still in the back there, thank you for that wonderful plug. I appreciated that somebody noticed. So MAVEN is the Mars Atmosphere and Volatile Evolution mission, and I'll tell you that the real difficulty is coming up with an acronym that everybody likes. I've taken grief from MAVEN because it's not a true acronym. The N at the end of MAVEN is the N at the end of evolution. But all I'll say is you should have seen the ones we didn't pick. Our goal is to look at the upper atmosphere. And you may not think that studying the upper atmosphere relates to the geology of the surface or to the potential for life, but in fact, that's the way we sold this mission as an astrobiology mission. We have a lot of evidence. You can see a picture in the upper left here for water having flowed over the surface on ancient Mars. Something happened because the climate, the environment today is cold and dry and not able to sustain the long-lived liquid water that would be required to produce a feature like that. So the question goes, where did the water go? Where did the carbon dioxide from an early thick greenhouse atmosphere go? And this has been one of the puzzles for years. There are two possibilities. It can go down into the crust and form carbonates and water deposits. And in the Martian meteorites, we see evidence for carbon from the atmosphere and the crust, but not in the amounts sufficient to explain that early thick atmosphere. It can go up to the top of the atmosphere and be lost to space. Here you can see a color representation of some of the measurements from the European Mars Express spacecraft that show ions being stripped away. What we didn't learn from that mission was what's the real escape rate today, loss out the upper atmosphere, and what has it been over time? How has it changed? What's the integrated amount of gas that has been lost? So what we're trying to do with MAVEN is to explore the upper atmosphere. It's the conduit through which gas from the atmosphere has to travel in order to get from the main atmosphere to be lost to space. And by understanding that, we can learn how much gas has been lost to space, what controls the habitability of Mars by microbes, what controls the history of water that has affected the geology of the surface. So it really is a geology and astrophysics mission. We're just doing it from a different perspective. As an aside, we're studying this really thin, tenuous part of the atmosphere, and I'm a professor in a geology department, so I really do connect it up. We think we have some understanding of the processes that play a role in the escape of gas, and we've learned this by looking at comets, by looking at Venus and Earth. We have the sun providing extreme ultraviolet energy and solar wind and solar energetic particles, high stream storms that can strip gas off the atmosphere, and we have a number of different processes by which the gas can be removed. And I'm not going to go through each one of these, but hopefully we've defined a robust enough mission that with the instruments we've sent to Mars, we can learn about these processes and about whatever else we find, because we've never really looked at this part of the Mars environment. And I'll I'll tell you, I've given the same talk for 10 years leading up to this, and the words that just came out are, I hope we have defined a robust enough mission. I'll tell you we have, and I'm going to show you some of the results. I forget that we're now in orbit and getting data and getting results. I gave the same talk for about 8 years. Now I have to change it every 6 weeks because of the new results we get. I want to show you one example of one process, just to give you an intuitive sense of how this works, and that's the ability of the solar wind to strip gas off the atmosphere. We're looking here at a computer simulation of what can happen. The solar wind is represented by these arrows streaming past Mars. The extremely thin, tenuous upper atmosphere is being stripped away by the solar wind as it goes by. It's going it's being stripped away by half a dozen different processes, but they all act together. Think of it as analogous to if you step out of the shower and step out into the wind, and the wind whips through your hair and dries it. That's sort of what's going on here. Mind you, this is becoming an increasingly theoretical construct for me. You're laughing. It breaks my heart. So we designed a spacecraft specifically to be able to address these questions, although it has a lot of heritage from previous Lockheed Martin spacecraft. This is the artist's rendition before launch. For scale, the high-gain antenna here is 2 meters across, so it's about that high. The high-gain antenna, the solar panels are fixed, and we have some instruments that want to be oriented relative to the sun, some relative to the solar wind, and some relative to the planet. So the spacecraft points at the sun, the instruments are fixed on it, and several instruments are mounted at the end of a boom down here that can be articulated in 2 directions and point anywhere we want. This lets us get all of the measurements we need. We have 9 instruments on the spacecraft, and I'll walk through them very quickly. I'm not going to dwell on them, but we have 4 instruments that were designed to measure the properties of the sunlight and the solar wind. And it seems odd that a Mars spacecraft has 4 of its 9 instruments looking at the sun, but it's so important to understand the energetic input into the upper atmosphere that we really need to do that. We have 3 instruments designed to look at the behavior of ions in the upper atmosphere, since we think that ion loss processes are responsible for most of the loss. One of them measures the electrons in the ionosphere, one measures the magnetic field, and one measures the composition, velocity, and direction of ions as they're escaping from the planet. And then we have 2 instruments designed to do everything else, and I labeled it neutrals and ions and evolution because these are really the workhorse instruments that tell us so much about it. We have a mass spectrometer that measures the composition of the upper atmosphere at the location of the spacecraft, and every orbit we pass through the upper atmosphere, so it gives us a detailed look at a point. And then we have an imaging ultraviolet spectrograph that can do global imaging of ultraviolet emission that tells us many of the same things but distributed globally. So this combination of detailed in situ and remote sensing is an incredibly powerful one. The mission we launched, we're coming up on 2 years ago now. It was a 10-month ballistic cruise to Mars, and orbit insertion was, coming up on a year ago with a 33-minute rocket motor burn. I'll tell you, this image is not to scale. The spacecraft is not quite that big. This one is to scale. This is our final science mapping orbit. At the highest part, we're about 6,000 kilometers above the surface, and we can image the whole disk. At the lowest part, we're 150 kilometers above the surface, and we pass through the entire upper atmosphere, going between 6,000 and 150. And then several times during the mission, we're lowering that lowest point to 125. And you may not think that going from 150 to 125 makes a big difference, but it lets us get the entire column of the upper atmosphere all the way down to the top of the well-mixed lower atmosphere. So it lets us connect up the upper atmosphere to the lower atmosphere. And then this orbit processes the gravitational forces from the sun, cause it to move. If the spotlight is the sun and my head is Mars, it rotates in this direction, and then it also rotates in this direction, so that over the course of the mission it sweeps out this complex pattern, but that lets us cover the entire three-dimensional region around Mars. We picked the size of the orbit and the inclination so that we would get the best coverage of that full three-dimensional region of space near Mars. So what I want to do now, that's all I want to say about the mission itself until the very end. But I want to tell you a little bit about some of the discoveries and about some of the paths that we're on right now. And I'm going to start right after we got to Mars. We had a totally unexpected encounter with a comet. We'd been expecting it for about a year and change, year and a half, but when we proposed the mission, it was unexpected. Comet Sighting Spring had an extremely close encounter with Mars about 4 weeks after we got there, and we went into, oh my God, this is going to kill us mode. We turned off all the high voltage, we turned off all the instruments, we phased where we were in that orbit so that for the 20 minutes we would hide behind the planet and be shielded from dust, and we timed it so that that was at the peak period of dust from the comet. And we turned the solar panels sideways to minimize our cross-section so that if there was dust, we'd have the least chance of getting hit. Fortunately, we survived that. As soon as the risky period was over, we turned back to Earth to see if we survived and to make sure that there were no problems with spacecraft systems. And then we turned on the instruments because we wanted to see what the comet did to Mars. And even though we weren't ready, we did a week of observations of Mars in order to see that. And the first thing we saw was this humongous ultraviolet emission. This is an emission spectrum in the ultraviolet. Just before the comet, that blue line. Just after, that red line. That's magnesium ions. Where does the magnesium come from? It's dirt from the comet. It comes in at 56 kilometers per second, hits the atmosphere, ionizes, vaporizes, and we see these ion features. In addition to seeing it in the ultraviolet, we saw it with the mass spectrometer. All of a sudden, magnesium, titanium appeared in the upper atmosphere. We detected 11 different ions: magnesium, iron, titanium, aluminum, and I can't remember the rest. What happened was the debris from the comet created a brand new layer in the Mars upper atmosphere, in the ionosphere. It's analogous to ones we see on the Earth, but it had never before been detected at Mars. So we were eventually able to start our science, and during one of those campaigns when we lowered that lowest altitude, what did we see? But we saw the same darn dust. Here in the mass spectrometer, you're seeing iron 56, 54 and 56. And up here in the static instrument, that's the one that measures the ion composition and velocity, the data is shown as a function of mass and energy. That blob in the circle is stuff at a mass of 55 to 60, so it's iron. So we're seeing the long-lived layer that must exist that wasn't directly related to a comet. And again, that's a fundamental discovery about the Mars upper atmosphere. The surprising one, that electron instrument that I described is able to work in a mode where it can detect dust impact on the spacecraft. If dust grain comes in and hits the spacecraft at hypervelocity speeds, it will vaporize, ionize, and for a brief moment change the electrical potential of the spacecraft. And that can be detected. That's what is seen here in the lab. That's what is seen here in the measurements from MAVEN. Each one of these lines, there's 100 there, represent a dust grain impact. And we see it all over the place. Why do you get dust at orbital altitudes? This is shown, by the way, as a function of altitude. If you can't read it, it's 0 to 1,500 kilometers. and solar zenith angle, which is how far off from the direction to the sun the spacecraft is. So the dusk side, the dawn side, all those red dots are dust grain impacts. The dust can be wafted up from below, which would be really surprising. It can come from Phobos and Deimos, which would be just as surprising, or it can be just interplanetary dust settling in on Mars, and that may be what we're seeing. Every spacecraft at Mars has been hit by this crud. We just happen to be the first ones to detect it. The last fundamental discovery that I'll talk about is the observation of a diffuse aurora around Mars. 3 minutes already? My God. I'm only going to go over by about an hour. I hope that's okay. Again, we're looking at the ultraviolet, and on the day side, you see ultraviolet emissions stimulated by UV light impact. On the night side, you see some of those same emissions, and there's no UV light. So it's caused by electrons and protons from the sun, from the solar wind, that hit the atmosphere and stimulate emission. That's what an aurora is. We're measuring it in the ultraviolet, but we suspect it occurs in the visible as well. There are certain wavelengths in the visible where aurora are seen. We saw this for 5 days in December, just before Christmas, and the IUVS lead looked at that and goes, my God, what's causing that? And he asked around, and the solar electron guy said, well, that's when we saw the biggest storm from solar electrons. It's exactly at the same time. So we're seeing aurora stimulated by storms from the sun. I'm going to quickly go through some of the main results because I really wanted to talk about the escape of gas from the atmosphere. We can image the planet, image the upper atmosphere here in atomic carbon, oxygen, and hydrogen. You can see that little red circle, that's the planet, and we're seeing stuff that's clearly in the upper atmosphere. These are the components of water and CO2 that we're interested in tracking. So we're seeing them on their way to escaping. Since I am running out of time, I'm going to go through this quickly. We can see the effect the solar wind has on the planet. The solar wind coming in from right to left. When it hits the planet, it creates a bow shock because it's hypervelocity speed, supersonic. And this is the average location. You can see the density increases given by that color. That is what really drives a lot of the escape. I'm going to skip by this because I want to tell you about this. We've seen how that drives escape. The forces from the solar wind create an electric field that drives stuff up. And you may have a hard time seeing these arrows, but the arrows show gas being driven this way and out the top of the planet. It really does go out the top. We've called that a polar plume. You can see that when we look at low altitudes and high altitudes. You can just see the energies of this on this axis. The energies are at thermal energies. And if you go up to higher altitudes, you see them at escape energies. So we're seeing the acceleration of ions, and we're seeing it escape. If we look at models of this process, it looks like this. It's the same driving out the top of the polar plume. Now, I think this looks like Nemo from Finding Nemo, but one of our scientists has likened it to a mohawk haircut. And we tried to figure out how we could envision this. This isn't quite it. It doesn't quite have the right character. This is a little too narrow, and we finally settled on Miley Cyrus. This is exactly what we're seeing. I'll just say, without going into it, that we've seen a couple of solar storm events at Mars, and we're able to see what the escape is from the planet. And my closing slide, since I'm out of time, MAVEN is 8 months into its mission. It is working great. The data are great. We have our first round of publications submitted. We're continuing our standard observations. We're continuing are special campaigns like the Deep Dip campaigns. And we just got approved for our first extended mission, which will begin as soon as the primary mission is over in mid-November. And I want to hark back to something else that Casey said. He has to go remind himself, he said, at Air and Space Museum of why he does this. All these science results, even though I'm a scientist and the lead of the project, I don't get to look at data. I'm caught up in budgets and planning and programmatics and mission sequencing, but we have a spectacular team that is doing an incredible amount of science. And to me, this is what it's all about, getting these science results and feeding it back to people like you who are interested. So I will stop there so we have at least a couple of minutes for questions. Thank you.
For our questions.
Looking ahead at a future of a colonized Mars, do you expect MAVEN to tell us something as to what it would take for Mars to be able to retain an atmosphere, or its inability to do so if we try to recreate it at some point in the future?
I've got a couple of answers to that, one of which directly answers and one doesn't. The first is that in some ways MAVEN is about how much gas has been lost, but it's also about how much gas has been retained. And even though you didn't use the word, if the gas has been retained somewhere on the planet, it might be released and we could terraform the planet. So in some sense, it's a mission about terraforming as well. The other half of the question that I'll answer is, what does it mean for radiation at the surface? Well, now we have radiation detectors, which is essentially what this is, in orbit, and we have one on the Curiosity rover on the ground, and we're comparing the two in order to understand what effect the atmosphere has and what effect storms can have. So again, it tells us, even though my interest is really the history of climate and what makes a planet habitable by microbes, it also tells us about what makes a planet habitable by people.
That's great.
People.
Keep up the great work here.
Thank you.
Do you, before the appearance of comet sighting spring, did you notice any changes before or after the encounter in the ionosphere of Mars, a shift of the F1 layer, anything of that sort?
Well, we saw the appearance of a new layer and then its rapid decay away. We were not prepared to take observations yet, so we got sort of a bare minimum, and the effects that it had were short-lived. It's an interesting experiment to have seen carried out, and we're still trying to figure out exactly what it means. The behavior of the ions was different from what our models predict. You know, different decay time, different relative abundances, and that tells us something of real significance about the chemistry of the atmosphere, but we don't know yet what that is.
Were any ions, can you tell if any ions were directed towards the surface?
It's hard to get from the ionosphere down to the surface. I don't think any make it under any circumstances.
So I'm a little bit curious about the 1-year primary mission. I seem to recall that Opportunity and Spirit were supposed to last 90 days, and now we have Opportunity is still here with us 10 years later. So I guess my question is, how long do you think it might MAVEN continue? I guess particularly I'm interested, as you do these deep dives down to 125 kilometers, how much delta V are you losing on basically aerobraking, and how much fuel do you have that you could maintain that orbit?
Those are very astute questions, and I'll start with why did we pick 1 year? And this is a PI-led mission, which means we had a strict budget cap, and it's a balance between, we'd like to go a long time, but to do that costs money. So what's the real length of time we need to make measurements in order to answer the science questions we posed? And that was 1 year. We picked that, and we fit within the budget cap. Now, we're going to get into an extended mission, and we're picking different additional science questions so we can justify going on. We carried enough fuel to recover from an off-nominal orbit insertion. That didn't happen, so all that fuel is still there, and we use that for longevity, we can last perhaps a decade. So we're going to be a long-lived orbiter, but you're right, the deep dips take a lot of delta V going down and up. We think we can do about 8 over the course of the mission before it would use up too much fuel. And when we're down at the bottom, that's when we experience the most drag. It is like aerobraking, and it reduces the apoapsis altitude. In fact, what day is today? Thank you. This past week on Wednesday, we carried out the first period correction maneuver to raise that apoapsis back up. That was an 18-minute burn to make up for all that aerobraking. It worked perfectly, no issues, no problems. But we have to do one of those after every 3 or so deep dip campaigns. So we'll have to do a couple more over the lifetime of the mission. As an aside, over that 10 years, we're going to do some great science. NASA wants us to survive because they want us to be a relay for Curiosity, InSight, Mars 2020, and we're happy to do that, but we still want to do our science.
Thank you very much, Doctor.
Thank you.